Okay, I think it works on YouTube. Okay, let's get started. Welcome to the second meeting and also the first background lecture for the PNS Modern SSD course. So before we get started, there was a question actually in the YouTube premiere for the first meeting, asking if it would be possible for other people outside ETH to participate in hands-on projects. So first of all, I would appreciate the interest in our course. And basically, we are planning to provide a live stream of all the background lectures as well as the learning materials on YouTube, as we are doing now. But we have not yet decided whether to publicize the hands-on projects because some topics can be highly related to ongoing research of the group. But certainly, we will discuss how we can provide an efficient way for other people outside the ETH also to participate in hands-on projects, if anyone is interested. Okay, so today, as a background lecture, we will discuss the three fundamental topics in NAND flash-based SSDs. SSD organization and request handling, NAND flash organization, and Beijing NAND flash operations. Okay, let's dive into the first topic. So recall the architecture of modern SSDs that we have briefly reviewed at the last meeting. A modern SSD contains multiple NAND flash packages. For example, this 1 terabyte SSD consists of 8 NAND packages, including the 4 at the bottom side, each of which has a 128 gigabyte capacity. There also exists LPDDR DRAM, whose size is typically 0.1% of the SSD capacity. So in this case, it's 1 gigabyte. And a powerful SSD controller manages the DRAM and NAND flash using multiple cores and hardware flash controllers to service the I/O requests from the host systems. Let me show you another organizational overview of modern SSDs that you can easily see in the literature. So we can classify the components in the SSD controller into 3 major modules. The first one is a host interface layer, HIL in short, which is responsible for the communication with the host system. The second one is a flash translation layer, commonly called the FTL, which is in charge of fundamental internal tasks to service a host I/O request while hiding the unique characteristics of NAND flash memory from the host system. In general, the core functionalities of HIL and FTL can be implemented as embedded software programs that run on the embedded cores inside the SSD controller. The last one is hardware flash controllers, which are responsible for ECC and data randomization, as well as the communication with underlying NAND flash memory. And each flash controller controls 1 or more flash packages, and we are going to take a deeper look into the organization of NAND flash memory soon in this lecture. On SSD's internal DRAM is used for various purposes, including host request queues, a write buffer, a mapping table, and metadata store. In this PNS course, we will basically discuss the details of each component, but let me review very briefly how an SSD handles a host request. So let's start with the write request, because for sure, you can read the data from an SSD only when you have written some data there. So first, every I/O request comes through the host interface layer, which is responsible for the communication with the host operating system, meaning that the HIL receives and returns a host I/O request via a certain storage interface like SATA and NVMe interfaces. A host I/O request should include request directions, meaning a read or write, the start address of sectors involved in the request, and the request size in the number of sectors. Here, the sector is commonly 512 bytes in size as a kind of a legacy of HDDs. But because most modern file systems manage data in 4 kilobyte block granularity, the sector offset and size are typically aligned by 4 kilobytes. And the data to write is usually first buffered in internal DRAM, And the FTL is responsible for managing this data buffer that can also store some recently read data as needed. So this DRAM cache is essential to reducing SSD level write latency. The write latency of a modern NAND flash chip highly depends on the chip's technology, but the page write generally takes about several hundreds of microseconds. So without a DRAM buffer, and if all the NAND flash chips are busy to handle previous write requests, another write must wait until the NAND flash chips finish the ongoing requests, which can expose the long write latency to the host system. So it is common practice to use a write buffer if internal DRAM is available, which allows the SSD to return a host write immediately after just buffering the requested data into the write buffer. The DRAM cache also enables a more flexible I/O scheduling. The read latency of a NAND flash chip is typically lower than 100 microseconds, which is several times shorter than the write latency. And a read request is performed in a synchronous manner, meaning that the host system is waiting for the completion of the read request. And it makes the read request much more latency sensitive compared to a write request. So for this reason, when there are enough space in the DRAM cache, prioritizing reads over writes can reduce user experience the I/O latency. Also, buffering data can be helpful for improving SSD lifetime. As we briefly discussed at the last meeting, a flash cell has a limited endurance, meaning that a flash cell cannot reliably store data after experiencing a certain amount of program and erase operations. So if a host write request hits the DRAM cache, in other words, if the previously requested data is to be updated with the new data before the SSD writes the old data to NAND flash memory, the SSD does not have to write the data, the obsolete data from the previous write request, which reduces the number of program operations actually performed. But I would say this may not happen so frequently, as data locality is not so high at the storage device level, since the I/O requests with high locality are usually filtered out by the host side I/O buffer, such as the OS level page cache. In fact, some studies actually assume a large DRAM cache inside an SSD without proper justifications, but in practice, the DRAM capacity is somewhat limited to, let's say, several tens of megabytes. This is because when sudden power off occurs, the SSD must be able to flush all dirty data into NAND flash memory to ensure data integrity, right? So increasing the size of DRAM write cache usually leads to increase of super capacitors to supply enough power for the SSD to reliably flush all dirty data, which in turn would directly increase the SSD price. In addition to that, even though a modern SSD contains quite a large DRAM, for example, whose capacity is about 0.1% of the SSD capacity, most of the capacity needs to be used for storing logical to physical mappings for address translation. So we are going to discuss this in more detail at the next slide. So after buffering the requested data, the FTL write the data into NAND flash chips with address translation. So address translation is necessary for out-of-place writes that are needed to hide the erase before write property. And as we discussed at the last meeting, a flash page cannot be overwritten, meaning that the page must be first erased before writing new data to the page. So suppose that the host system keeps updating logical block 0, the first logical block in the storage device view of the to the host system. For the first line, we can simply write the data into the first physical page in the SSD for sure. But for subsequent updates on the same logical address, we cannot overwrite the physical page because erasing it, so unless we erase it because of the erase before write property. So an FTL writes the new data in other pages that had been erased before, while marking the page with the old data as invalidated. And since the logical page address and physical page address no longer match each other, the FTL must maintain the logical to physical mapping, meaning that the information about which physical page stores the logical page data in order to service the future reader request on the page. And typically, except for some SSDs with very high resource constraints, the mapping granularity is 4 kilobytes. In other words, even when the actual size of a physical page is larger than 4 kilobytes, let's say 16 kilobytes, it is common practice that the SSD deals with host IO requests in 4 kilobyte granularity to efficiently handle host IO requests typically aligned by a 4 kilobyte block. So we will discuss this also in more details in another background lecture. So the point is, assuming a 32-bit architecture that requires 4 bytes to store mapping information of 4 kilobyte data, the memory capacity required for L2P mapping is around 0.1% of total SSD capacity. Okay, so while handling host requests, some other internal management tasks can also be performed as needed. For example, if the SSD is running out of free pages that had been previously erased, the FTL must perform garbage collection to reclaim free pages that will be used for future writes. So basically, garbage collection selects a victim block, first selects a victim block, and read all valid pages in the block and erase the victim block. Also, sometimes the FTL needs to perform rare labeling if it detects certain blocks that are experiencing a high number of P cycles compared to the other blocks. And this is essential to enhancing SSD lifetime, as we discussed at the last meeting. And one representative way of rare labeling is hot-cold swapping, which moves infrequently accessed data, in other words, cold data, into a block that has experienced the high P cycles. So because the moved data is infrequently accessed, it would likely stay in the target block that has experienced the high P cycles. So the increase in the P cycle increase for the block can be avoided. And the FTL should also care about pages that have a long retention age, meaning the pages that had been programmed a long time ago, as a flash cell leaks its charge over time, which is called the retention loss. And if a page's retention age is higher than a certain threshold, the FTL usually copies the page's data to another free page to reset the data's retention age. Okay, finally, the data is sent to the flash controller to issue a program command to the target NAND flash chip. Before that, the flash controller randomizes the requested data in order to avoid worst case data patterns that can lead to a significant number of errors. After data randomization, the corresponding flash controller performs the ECC encoding that generates some redundant information called ECC Parity, so that the SSD can detect and correct errors in future reads using the parity data. Since modern NAND flash memory is significantly error-prone, so it is common practice to use a very strong ECC in modern NAND flash-based SSDs, which can correct several tens of row-bit errors in a 1 kilobyte data chunk. Finally, the flash controller issues a write command to the target flash chip. Next, let's see how our reader is.
One question.
Sure.
Does the redundant information I store depend on the data type, or is this in general 72 bits for 1 kilobit?
Yeah, so definitely, yeah, that's a very good question. So when you generate the ECC parity, there could be some, multiple ways for sure, but generally it generates some parity checks based on the programmed data. So yeah, it depends on the data pattern for sure.
Okay, thank you.
Yeah, thanks. Yeah, but I would like emphasize again the data, the generated data along with the raw data. No. So I would emphasize that the ECC, the order of ECC and randomization. So NAND flash memory first randomize all the data to be programmed, and after that it perform ECC. So if this order is somewhat changed, right? So is the opposite, then it might be very problematic because the randomizer. So if the raw bit error occurs, then it changes the ECC. So the randomized pattern, right? And if the raw data, if we perform the first the de-randomizing, and when you read the storage data, then it changes significantly the encoded ECC parity, right? Yeah. So yeah. So as long as the randomizing algorithm is somewhat able to preserve its randomization mechanism even with some raw bit errors. So yeah, it is a it makes much more sense to perform the first the randomization and generate the ECC parity based on the randomized data. Okay. So next, let's see how read request is handled, which I believe is relatively simple. So once the host interface layer receives a read request, the FTL first needs to check if the requested data exists in the right buffer. And if so, the SSD can immediately return the read request with the buffer data. However, a host read request can be involved with several pages, as the host system always tries to read the same amount of data with a smaller number of requests, meaning that the host system always tries to merge small reads to a fewer number of large requests, if possible, in order to minimize the communication overhead between the host system and the SSD. And in such a case, the SSD can return the read request only after all the requested data is ready. And if the requested data does not exist in DRAM cache, the FTL needs to figure out which physical page stores the requested logical block by querying the logical to physical mapping table. And after that, the FTL transfers the request to the flash controller so that the controller can read the raw data from the target NAND flash chip. The flash controller first performs ECC decoding using the ECC parity and de-randomizes the decoded data to get the original raw data. And in fact, ECC decoding can frequently fail due to a large number of errors in the read data. And usually the SSD then retries a reading of the page with adjusted reference voltage, which is called a read retry. And if even read retry cannot reduce the number of raw bit errors, the SSD may perform soft decision ECC like LDPC, which is a more powerful ECC with probabilistic approaches. Okay, so far we briefly discussed the SSD organization and request handling process, top to bottom, from the host interface layer and to underlying NAND flash memory. So before we move on to the NAND flash organization, do you have any questions? Sorry, there was some interrupt, and yeah, so there is actually a question. from Karthik is parity written along with the data into storage or buffered then moved? Yeah, it is a very good question. Actually, yeah, the parity data is stored into the NAND flash memory along with the raw data, the requested data, so that whenever we access the stored data, the parity values would be also read together and to be used for ECC decoding. So there is some spare cells along with the page, or yeah, we'll cover for this very soon in this lecture. Yeah, anyway, there is some spare cells to store some such dedicated metadata to a specific data. Yeah, which is called OOB, out of band area. Yeah. Okay, so yeah, basically the answer is yes. They should be the parity should be stored along with the raw data at the same position. Okay. Let's dive into then the second topic, some details of NAND flash memory. So we will discuss how typical NAND flash memory is organized, bottom to top, and from a flash cell to a NAND flash package, and some characteristics of NAND flash memory that are introduced by the organization. Basically, a flash cell is a kind of a transistor that consists of a control gate, source, drain, and substrate. And as you know, a transistor can operate as a switch, meaning that when you apply a voltage between the source and control gate of a transistor, it can operate as a, oh, sorry about that. Yeah, it can operate as an open switch or a resistance depending on the applied voltage and the threshold voltage of the cell. So the key difference between a flash cell and a regular transistor is that a flash cell has a special material called a floating gate or charge trap. So 2D NAND flash implements the special material using a floating gate, but it is also one of the mainstreams for 3D NAND flash memory to implement the material using a charge trap. So the physical characteristics of these materials are quite different from each other. And so the NAND flash memory based on different technology also exhibits some different physical characteristics. But yeah, today we will review NAND flash organization with 2D technology to make it easier to understand. So the spatial material in floating gate in 2D NAND flash memory can hold electrons or charge in a non-volatile manner. In other words, the cell can retain the electrons inside the floating gate even when there is no external power supply. So to inject electrons into the cell's floating gate, we need to apply a very high voltage, let's say higher than 20 volt between the control gate and substrate, which introduces tunneling effect that moves electrons from the substrate to the floating gate. We call this process a program, and programming a cell increases the threshold voltage of the cell. And we can determine whether or not a cell is programmed by applying the read reference voltage to the control gate of the cell, which is between the two threshold voltage values. So the cell operates as a resistance when the threshold voltage is lower than the read reference voltage, or an open switch otherwise. And it is also common to encode the lower threshold voltage level as bit data 1 for a single level cell NAND flash memory that stores 1 bit in a single flash cell, for example. And to eject electrons from a programmed cell's floating gate, which we call erase, we need to apply a reverse high voltage between the control gate and substrates. So before we move on other higher levels of the organizations, let's review some basic characteristics of a flash cell. First, a single flash cell can store multiple bits, and we call such an approach a multi-level cell or multi-leveling technique. As we discussed, a program operation increases a cell's threshold voltage, while an erase operation decreases the cell's threshold voltage by changing the amount of electrons in the cell. And if we can more precisely control the amount of electrons and use more read reference voltage values, it allows us to make multiple distinguished states with a single cell, each of which is used for encoding a possible bit pattern of the stored bits. For example, in this figure, the cell is designed to store up to 2 bits by creating 4 voltage states from 10, 00, 01, 11. And each of which represents one of all the possible bit patterns from the 2 bits. And second, ideally, as a non-volatile memory, a flash cell is supposed to be able to keep the charge inside its floating gate without power supply, but unfortunately, it leaks electrons over time, which is commonly called a retention loss. As the figure shows, after a year, the amount of electrons decreases, which in turn decreases the cell's threshold voltage level. And a very long retention time can decrease the threshold voltage even to be lower than the reference voltage, which in turn introduces a retention error in reading the cell. And finally, a flash cell has a limited endurance, meaning that it cannot reliably store the data after experiencing a certain number of program and erase cycles, as we discussed at the last meeting. So for example, 1 year retention at 1 kp cycles would not incur a retention ladder, even though there should be some retention loss. But if the cell had experienced the 10 kp cycles, it becomes much easier to leak the electrons, which would likely cause a raw bit error after the same amount of retention time. Okay, so let's dive into how these flash cells are organized in NAND flash memory. So multiple flash cells are serially connected, forming a NAND string that is connected to a bit line. And as you can see, the cell structure is effectively the same as a NAND logic. And that is the reason why we call this NAND flash memory. And here we need to access only a single cell within a NAND string at a time. And we can do that by applying a proper value of voltage to other non-target cells, which is high enough to turn on any flash cells regardless of their current threshold voltage. It means that the stored values in other cells cannot affect the state of the NAND string. So there are a huge number of bit lines in NAND flash memory, more than 100,000. And a word line connects the control gates of all the cells at the same vertical location in different NAND strings. It means that a NAND flash memory always applies the same voltage to all the cells connected to the same word line, which makes the cells operate in parallel to read or program data. So NAND flash memory performs a read and write operation in a page granularity, and the page size is equal to the number of cells connected to a word line. And typically, it is 16 kilobytes plus some additional bytes to store metadata related to the page, such as the ECC Parity. So because the additional cells are also connected to the same word line, whenever we read the requested data, the parity data, its parity data should be also read at the same time. And in the case of MLC NAND flash memory, multi-level cell NAND flash memory, the cells connected to a word line can store multiple pages, or we often just simply say a word line can store multiple pages. For example, in 2-bit MLC NAND flash memory, this single word line, a set of cells connected to the same word line, can store up to 2 pages, commonly called the least significant bit page and the most significant bit page, or just LSB and MSB pages, respectively. And cells in the NAND string that are connected to the same word lines comprise a block, the unit of erase operations. So the block size should be the same as the multiple of the number of word lines and the number of bits stored in a single cell. And as we discussed, the program and erase operations are unidirectional, meaning that programming and erasing a cell can only increase and decrease the cell's threshold voltage, respectively. Also, a NAND flash memory performs a program operation at a page granularity, and a page program cannot change 0 cells to 1 cells in the example we have discussed in the previous slide. So we always need to erase the page before programming it, which is called the erase before write property, right? And the erase unit is a block which makes the erase latency several times longer than other operation because it involves a lot or way more cells in operation. But such a bulk erase increases the erase bandwidth. Since a block is a modern block in modern NAND flash memory has hundreds or even thousands of pages. So concurrently erasing such a large number of pages at once outweigh the increase in the erase latency. However, the real problem is that such a bulk erase makes it very inefficient to perform an in-place write on a page, meaning erase the page and updating the page with the new data. So the SSD controller commonly performs out-of-place writes and garbage collection. So we will cover it more in depth at another background lecture. Okay, and a large number of blocks, more than let's say 1,000 typically, it constitute a plane while sharing the same bit lines. Since the bit lines are shared by all the blocks in a plane, we need to make sure that accessing a word line in a certain block neither affect nor is affected by the cells in other blocks. And to this end, on the top and bottom of each NAND string, there are string select line, or SSL in short, and ground select line, GSL in short, which can effectively disconnect non-target NAND strings from the corresponding bin lines by applying a lower voltage than the threshold of this SSL transistor and GSL transistor. So when you apply the lower voltage than the threshold, this SSL transistor and GSL transistor should operate as an open switch. So it effectively disconnects this bin line, which should not be activated from the corresponding bit line. So in other words, we can activate only one block in a plane by applying a high voltage only to the target blocks SSL and GSL, while just leaving the SSL and GSL of the other blocks to be floated. And a NAND flash die, or often also called a NAND flash chip, contains multiple planes, 2 to 4 planes, for example. And this is a picture of a 2D NAND flash die that is fabricated in a 21 nanometer technology node and contains 4 planes, page buffer, and other peripheral circuits, including row and column decoders. So planes in a die typically share the decoding logic, so they can concurrently operate only in limited conditions. For example, only for the same type operation at the same word line offset. So this, meaning that you can regard this line as a single page, and we can make all the planes concurrently operate only for operation on the same page offset in the planes. Okay, and this is called the multiplane operation, and we will also cover this with more details in a background lecture later. And please note that this is a die, which is different from a NAND flash package. A NAND flash package, in fact, commonly contains multiple dies that can operate independently of each other. Okay, now we are going to review the basic operation in NAND flash memory. And before that, any burning questions? Okay, is there any Q&A session from YouTube? Ken from YouTube? Okay. Yes, if you want, we can have a Q&A session at the end of this background lecture. But if you have any question, yeah, you can just leave in YouTube chat so that I can check it time to time during the lecture. Okay, thanks. Okay, before we dive into more detailed NAND flash operation, let's take a look at this figure. And if you read the papers about NAND flash memory, I bet you will see this figure in almost every paper. And this figure shows the threshold voltage distribution of the cells in a programmed page or block. So actually, this figure contains many pieces of information. So in fact, this is a graph that plots the number of or the fraction of flash cells in a programmed page or block that have a certain threshold voltage value. So each coordinate x, y indicates that there are y cells in the page or block whose threshold voltage level is x volt. And why do we show the distribution? It is because there are significant variations in physical characteristics across the cells. So some cells are more easily programmed or erased, while some others can be very difficult to program or erase, which makes it practically impossible, I would say, to make all the cells have the same threshold voltage level. So yeah, the only way to, not only way maybe, but a very efficient way for this situation is showing the distribution of 100,000 cells. Okay, and you may notice also that the two threshold voltage states show almost the same shape, but they should be different unless we write perfectly random data to the page or block, right? Because this is distribution. And the reason is that, as we discussed in previous slides, every data needs to be stored after randomized for better reliability. Yeah, I think we can discuss this with more details since we now know the organization of NAND flash memory. And in fact, there are many reasons why we should randomize every data stored in NAND flash memory, but let me explain it with the most intuitive example, I believe. Suppose only one cell in a NAND string is programmed while the other cells in the NAND string remained erased. Then the only programmed cell whose threshold voltage is increased rapidly leaks the charge inside its floating gate due to the huge voltage gap between two cells, between adjacent cells. And it in turn likely causes a retention error more easily. To avoid such a situation, in practice, every data needs to be randomized in vertical direction, and also actually the horizontal direction, which almost so the randomization should almost evenly distribute programmed and erased cell within a page or also in a block, regardless of the original data to be programmed. So if we even when we program all zero data, when you read the raw data without de-randomization, so meaning that directly from the NAND flash chip, then you will see the data is a completely random pattern. Okay, and this is the threshold voltage distribution of a triple level cell, in short TLC, NAND flash memory, where a single cell can store 3 bits. So basically, to store n bits in a single flash cell, we need to make 2 to m threshold voltage states. However, since the voltage window is limited, So we needed to narrow each threshold voltage state so that all the states can fit into the limited voltage window. While
I have
also
one question.
Sure.
Why is the bit order not descending, but like pretty random? Because you have 0, 0, 0 in the middle and 1, 1, 1.
So you mean this encoding, right?
Exactly.
Yeah, exactly. So yeah, that's actually a very good question, and I quite happy that you noticed that. Yeah, so we will cover for in the following slides. So can you please wait a moment?
Okay, thank you.
Yeah, sure, thank you. Okay, and while guaranteeing, yeah, where are we? Yeah. So because the threshold voltage window is limited, yeah, we needed to narrow each threshold voltage state so that all the states can fit into the limited voltage window, and while also guaranteeing sufficient margins between adjacent threshold voltage states. And providing sufficient margins is really important because the threshold voltage level of a cell changes over time after programmed due to retention loss, meaning that the threshold voltage states are shifted and widened after programmed. I would like to also emphasize that the threshold voltage states are not only shifted, but also widened over time. Since some papers assume that these threshold voltage states shift very nicely, keeping their shape perfectly. I believe the purpose is to ease understanding, but yeah, it is not the case in practice since the physical characteristics of a cell significantly vary, meaning that some cells much more easily leak their charge, while some cells is quite robust to the retention loss. Okay, and if a cell's threshold voltage level moves beyond the corresponding read reference voltage, reading such cell incurs a bit error. So the narrower the margins between adjacent threshold voltage states, the lower the reliability of the NAND flash chip. This means that advanced MLC technique can achieve high density, but it comes at the cost, a significant cost of low reliability. Okay, let's dive into how NAND flash memory programs a page. Here we assume a single level cell NAND flash memory that stores a single bit per cell. So the words word line and page can be used interchangeably, right? So to program word line K, so this is our target word line. And first, we need to apply proper voltages to each word line in the block, such that all other cells or non-target cells operate as a resistance. And you can see the VCC and VPass to all the other word lines, which are just enough to turn on the non-target cells, while the program voltage, VProg, is applied to the target word line K, which is much higher than the other voltage values. Okay, with such a word line voltage control, the block can be described like this, as all the cells other than the target cells will operate as a resistance. And together with the word line controller, we need to also control the voltage of all bin lines in order to program the given data values to the target cells. Here you can see the bit data, 0 and 1s, that needed to be programmed to the respective cells. So the question is, how can we program different data for the cells that are actually connected to the same word line? So we can do that by selectively charging bin lines depending on the data to program. So if we charge a bin line to VCC, it boosts up the substrate's voltage, which reduces the voltage difference between the control gate and the substrate to be lower than the voltage level required to program the cell sufficiently. So after this, then let's see how the threshold voltage distribution of this page changes. So because all the cells of a page should be first erased before programming, we must see only one threshold voltage state at the beginning, right? You may expect the distribution somehow nicely change like this, but reality is not so beautiful as in many cases. Actually, it happens something like this. Why is that? It is because some cells are very difficult to program, while others are extremely easy to program. So to make a desired threshold voltage state shape, it is a common practice to use the incremental step pulse programming scheme, or ISPP in short. The basic idea of ISPP is to gradually increase the programming voltage and repeat multiple program and verify steps. So we can see the difference, a different voltage is now being applied to the target word line in this figure, vprog 0, which shifts the threshold voltage state in a relatively smaller amount. And the NAND flash chip stops applying the voltage and verifies all bin lines to check whether each cell has already been programmed enough by the first step. And if it finds such cells, the corresponding bin lines are charged in order to inhibit the programmed cells for the next programming steps, meaning that to prevent the programmed cells from being programmed further. After that, the NAND flash chip again applies the program voltage with a little bit increased value, says vprog 1, so that it can move the threshold voltage states a little bit more. And by repeating this, we can finally get the target threshold voltage states in a good shape. Okay, next let's discuss the page read mechanism. Here we can see the data programmed in the cell 0, 1, 0, 1, 0. And basically the word line control is the same as program operates, except that we apply read reference voltage to the target word line, which is between the threshold level of erase states and the program states. Okay, bin line control is different from program operations, as we need to charge all the bin lines. Then, depending on each cell's data, meaning each cell's threshold voltage level, the cell would operate either as a resistance or as an open switch, which makes differences in the current that flows through each bin lines. If no current flow, the bin line as the threshold voltage, the threshold voltage is higher than the read reference voltage, it reads as 0. While if the current flows through the bin lines and the NAND string, the cell reads as 1. And for sure, the opposite way of encoding is possible with a different implementation of a sense amplifier that is connected to each bin line. But this encoding scheme is, I would say, more common in commodity NAND flash memory. Okay, let's dive into a more interesting case, multi-level cell NAND flash memory. Here, each cell stores 3 bits, and we are going to see the case of reading the central significant bit, CSB in short, which is the middle bits within the 3 bits stored, which I highlighted using red or blue colors, depending on their values. Okay, basically, to read a multi-level cell page, we need to sense the page in multiple times using different read reference voltage values. Here, we should use the reference voltage values whose 2 corresponding threshold voltage states represent different bit values, right? So you can see, so based on these 3 highlighted reference voltage, the CSV bit value is changed, right? Then what if we want to read the MSB page? The answer is we need to use BREF2 and BREF6 because okay, so this is somewhat poorly located because based on these 2 read reference voltage, the MSB bit, the first bit within the 3 bits, the value is changed, right? So for these first 3 states, there is no change in the MSB bit data. But yeah, so this is the borderline, right? Okay, let's go back to the example for reading the CSV page. Okay, this shows the sensor data by using BREF5, based on based on the stored value. So here we should see the threshold voltage state of each cell, not its CSV data, bit data, because the sense data is determined by the cell's threshold voltage level and the read reference voltage applied to the cell, right? And this is the results when using BREF3, and this is the result when using BREF1. And these data are stored in the latching circuit, temporarily stored in the latching circuit of the page buffer inside the chip. And finally, the NAND flash chip can get the stored CSV data by performing XOR operation with the results with the sensor amplifier circuits. So here, the 3-bit XOR results 1 if there are odd number of ones and 0 otherwise, right? And we can see the final XOR results of the sensed data is the same as the stored data. So here are some takeaways that we can get from the read mechanism. So first, MLC NAND flash memory requires an in-chip XOR logic somehow, as well as the latching circuit to temporarily store multiple sensing data. And second, the bit encoding scheme. So here is what I mentioned. So bit encoding scheme affects the read latency of a page. So for example, let's compare the number of sensing steps required for reading an LSV page under these two different encoding schemes. So under the first encoding scheme here, which is shown in top figure and was used in actually previous slides. Sorry. Yeah, 2 sensing steps are required using BREF0 and BREF4 respectively. So you should check. So we are now using reading LSB. So you should check the reference voltage where the corresponding bit value changes, right? And you can see the only BREF0 at BREF0 and BREF4 there is changes in LSB bit data. And how about in case of the bottom figure? We need to first use BREF0, right? And BREF2, and also BREF4, and BREF6. Sorry. Right. This means that the second encoding scheme, when it needs to read the LSV page, it requires 4 sensing steps, which doubles the number of sensing steps compared to the first encoding scheme. Right. So which one would be better? So I would say the first encoding scheme is much more widely used to minimize the latency variation across the pages sorted in a word, right? But actually, the other reason is this encoding scheme may also affect the reliability, as the higher the number of sensing steps for reading a page, the higher the number of errors in the page read, because the errors in each sensing step using different read reference voltage would be accumulated to the final results. So this means that if there is no proper optimizations, the bottom encoding scheme would introduce much more errors compared to the first encoding scheme when reading the LSV page. However, on the other end, in the case of reading MSV page, the first encoding scheme requires 2 sensing steps again, right? So using this BREF2 and BREF6, while the second encoding scheme requires only a single sensing step. So despite the high latency and reliability variation, the second encoding scheme could be also beneficial for in case of reading MSV pages, providing a low read latency and better reliability. So yeah, so meaning, so my point is that sometimes for a specific application or specific use cases, for example, if there is an application which needs a significantly high reliability and low latency compared to other application, we can actually exploit this performance and reliability asymmetry, right? Because we, if it is possible, we may store the important the reliability and performance sensitive data only using MSB page with this, I would say, asymmetric encoding. So, and I personally believe that this is this can be an interesting topic to explore. And yeah, so this is one of the topics we will suggest as the hands-on project for you. Okay, so yeah, this is the end of today's background lecture that I have prepared. So do you have any questions? So and yeah, did the explanation answer to your questions, David?
Yes, this makes sense. Thank you.
Thanks. Okay, so actually there is some questions. If we needed, Karthik, if we needed to change it just to 1 byte in page X, where does the byte get updated before it return back to a new place? Yeah, actually, it's a very good question. So, yeah, so this is, I would say, mismatches between the I/O units. So I/O unit mismatches between host system and NAND flash memory, let's say. So for example, if a part of page needs to be updated, then it's somewhat difficult to directly update the data into the corresponding physical page because yeah, NAND flash does not support overwrite, right? In that case, we usually need to read the page to the temporal buffer and update the parts, requested parts, and rewrite the data to another free page, which has been erased before, which it means that a single update of very small data incurs one read operation and one new program operation, meaning that the significant performance and also lifetime overhead. So to avoid that, there is an industrial standard that the host system should issue the write request at the minimum unit of 4 kilobytes. So when you trace the I/O request from a host, for example, Linux host system, so recent Linux host system, you can see only the I/O request in size of 4 kilobytes. Okay. Yeah, and definitely this is also a very important topic related to the mapping schemes also. So, and we will cover for this topic in upcoming lectures. Thanks for the question. Okay, from what I know, MLC or so can. From what I know, MLC or multi-level cell is 2 bits per cell and TLC is 3 bits per cell. So on and so forth. Yeah, exactly. But is it any physical limit for the threshold voltage? Physical limits for the threshold voltage. Yeah, so as I explained, I think the constants of threshold voltage, right? And as I explained, we needed to narrow each. So we need to ensure that all the. Okay, let me put this way. Okay, so there is a limitation of threshold voltage window. So we cannot increase we cannot increase the threshold voltage of a cell as we want. There is a limitation, right? And it is I call that threshold voltage window, and we needed to ensure when we develop a multi-level cell NAND flash memory, we need to ensure all the threshold voltage states fit into the limited threshold voltage window. And as I explained, we need to also ensure that we provide sufficient margin between adjacent threshold voltage states, because the threshold voltage states shift and widened over time due to retention loss or other cell-to-cell interference and other disturbances. So yeah, yes, it is correct. So we use the term MLC to typically refer to the 2-bit multi-level cell, and while we use TLC or QLC for referring the memory technology that stores 3 and 4 bits in a single cell respectively. Okay, and value parity shall be programmed to the flashes so that the ECC could be both a payload and parity for the error correction. Exactly. Okay. I think we addressed all the questions. Okay, so today we have 2 required readings. First, we ask you to read this book chapter for introduction and section 1, which provide a good overview of SSD organization and NAND flash memory. And the second one provides a comprehensive background of a 3D NAND flash organization and detailed read mechanism and a new optimization technique to reduce the read latency by optimizing read retry operations that I very briefly mentioned in this lecture. Okay. And we also recommend you read 2 additional papers published in prestigious conferences in the field of computer architecture and systems. The first paper introduces a new internal I/O scheduling algorithm in modern SSDs to provide high performance and also high fairness when multiple applications share a single large capacity SSD, actually which happens quite frequently in modern computing systems. The second paper provides a good review of SSD internals and proposes an architecture that self-manages various SSD management tasks to provide a high level of quality of service performance. Okay, so this is all from my side. Any question or comments? Okay, yeah, can I see any question? So yeah, I think it is a good time for us to wrap up this meeting. Okay, thank you for joining the meeting. And thank you also folks in YouTube. Okay, let's meet next Wednesday and take care.
Goodbye.
Bye.
Thank you. Goodbye.